And if you have multiple bridges in there, what can happen is that in each loop you have to create additional copies. And so each packet here may create additional copies. You know, if you have multiple ports being broadcast, so what you can just fill up your network in no time, just conventional here. So the problem here is the loop that occurs, and you know, that's the same with the problem of the loop. Well, the problem is the loop. What's the solution? Well, one needs to do something else. This clearly indicates the learning bridge algorithm works well, but it creates loops. It does not prevent loops from occurring. So, you know, that's the solution is to do something where loops like this do not happen. Meaning, if the same LANs are connected by multiple bridges, only one of them will forward packets between the LANs. The other one will be disabled. And that's essentially, if you're thinking about it, it's like the selection of a routing protocol. So the way it's done with bridges, with LAN switches, it's done with the spanning tree algorithm. Yeah, so it's an algorithm that builds a spanning tree which involves the bridges. Yeah, so the nodes of the spanning tree are the bridges, and the edges go from bridge over a LAN to another bridge, or only from a host to a LAN to a bridge. Now think about several hosts being attached to LAN. So this is a tree here. It's a directed tree. The root, you can tell here, yes, the direction down. This goes up, up. Here, bridge 3 is the root of the tree. And now the rule is this: bridges only forward frames along edges of the spanning tree. Now each bridge knows which of its ports is part of the spanning tree. This bridge knows that this port here, the port going to LAN 2, is part of the spanning tree, and this one is not part of the spanning tree. And what the bridges do is they never forward traffic on ports that are not part of the spanning tree. And you know what you see now is that, you know, here look between LAN 5 and LAN 2. There are two bridges, bridge 3 and bridge 4, being both connected. But only bridge 3 passes traffic through. Bridge 4 does not pass traffic because this link, this port from bridge 4 to LAN 2 is not part of the spanning tree. That breaks the cycle, solves the problem. And so the spanning tree protocol is just an algorithm that sets up this tree in a distributed fashion. That's essentially it. Spanning tree algorithms are very nice. There's something just beautiful about them. They're simple and just converge quite nicely. Now, so that's then the idea, yeah? So bridges that run are called, okay, so bridges that run, kind of this word, transparent bridges, I throw it in because it's still being thrown around. Now, the spanning tree is established using messages of a protocol, the 802.1d protocol. That's the spanning tree algorithm. The messages that are being exchanged, they're called BPDUs, Bridge Protocol Data Units, and those are the packets that we will be observing in the lab, in that one. You will be observing BPDUs, yeah, and that's why you know why we use bridge and not LAN switches, because that's the protocol. Everything is written in terms of bridges. So what I'm going to do today is just explain how the bridge, how this spanning tree algorithm works, and then we can compute an example of this here. It's set up. All right. So these are the BPDUs. Yeah, these are kind of the destination MAC, source MAC, and then there is the configuration information. Yeah, there's also kind of the protocol identifier is actually part of the header. So the fields that are relevant to us are these four fields in the BPDU. There's a root ID, and ID means ID of a bridge. Each bridge has an ID. There's a cost, this is the cost, it's the same, it's the number of hops from a node to the root. The root is the ID of the root of the spanning tree. Yeah, it's the root ID. If in this case here, bridge number 3 is the root of the tree. So if everything is converged, number 3 should be written in here. Cost is the number of hops that the bridge has to the root. Then there's the bridge ID and the port ID. This is the ID of the bridge that sends this message. And this is the port through which the bridge sends this message. So what this message here means is, hello, I'm bridge ID, this is my bridge ID, I'm the sender, I sent this through my port with this ID. I believe that this ID is currently the root of the tree. And the number of hops that I traverse is given here in terms of cost. Now, cost can be something different, but it's usually the number of hops. So that's each bridge sends out these messages, and this sets up the spanning tree. The spanning tree that minimizes the cost of each bridge to the root. So each root tries to find the shortest path that it has to the root. That's what the cost. Yeah? And so you're thinking about cost like this has a flavor of distance vector somehow. And that's exactly the way you have to think about this. It's essentially just a distance vector protocol. It works that nodes receive these bridge IDs, and based on this information, they calculate their own distance. But the only thing that they do is they calculate the distance only to the root. It's not a point-to-point routing algorithm. It's only to one point. You just have to find the place to the root. That's it. And so there's not a lot of traffic that takes place. So with the BPDUs, they accomplish a number of things. Number one, all bridges agree on a single bridge to be the root. They all agree, and the root is very simple. The bridge with the smallest ID, that's the root. The name starts with a Z, you're less likely to be the root. If the name starts with an A, you're most likely to be the root. That's cannot be simple. Then the nodes, the bridges use the BPDUs to calculate the distance of the shortest path to the root. And the root is called, and again a little bit more technical, it's called the root bridge. The root of the tree is the root bridge. And you see that the cost is sent in the messages. So if I add a 1 to it, if I receive a message from some other bridge, I add a 1 to it, that's my cost, the root. Then each bridges determine for each LAN, bridges elect a designated bridge. That is the bridge that forwards traffic from this LAN in the direction of the root. Forget. This is a bridge on a LAN that sends traffic downwards. The traffic is coming from the upstream to the root to downwards. Give you this example here. That's the election here. For LAN number 1, the traffic that comes down from the bridge, one of these bridges connected is the designated bridge for that LAN. In this case, this bridge number 5, this will be the designated bridge. It will be covered, it's not completely clear. I've not explained how the algorithm works, I just covered the outcome. Because we have to go from this abstract picture into something where you exchange protocols and something then converges. Alright, so that's the one. The designated bridge will forward packets towards the root of the bridge. Okay. Yeah, so that's the one. If there's traffic down here on LAN 1, yeah, the designated bridge forwards traffic out. This bridge will not forward traffic towards the root, this one also not. So that's for each LAN we get a designated bridge. For each bridge has one port. Each bridge is somehow connected to the spanning tree. Can have a link. It always has a link up, and may have a link down. the port that has the link up, that is called the root port. That is the port that gives the best path to the root. That's how it works. And so, the last piece is, but this is already a result from this and this, the algorithm, the BPDUs, will be used to select the ports that are included in the spanning tree, which is pretty much this. If a bridge is a designated bridge, that port is called, designated bridge on a port. The root ports, these are the ports that are part of the spanning tree. Everything else is not part of the spanning tree. That's it. Yeah? We'll see how this. Again, no, let's go. So now we're going deeper into the terminology of the algorithm. So bridges have IDs. The bridge ID is composed of a higher order priority field and a MAC address. And typically, you pick the lowest MAC address of all ports of the switch have a MAC address. You're having an Ethernet switch with 48 ports. They all have MAC addresses. The smallest MAC address makes up the lower order 6 bytes of the bridge ID. The higher order is the priority. Priority means something that the configurator that the administrator sets. Because I know the smallest bridge ID becomes the root. So if I set this number high, that bridge is unlikely to be the root. So I can somehow control the position of the root. If I have a fast switch, 10 gigabit switch, I want that one to be the root, not the little hub, kind of a little switch, the $50 Linksys switch that sits somewhere in the corner. Because the root gets more traffic than other bridges. The root bridge gets the most traffic. Let's see. Each port of a bridge has a unique identifier. That's called the port ID. Okay. So root bridge. I already see that the root bridge is the bridge with the lowest identifier. Let's see. Then there's a root port. Each bridge has a root port which identifies the next hop towards the next hop from the bridge to the root. That's kind of the direction of the shortest path. More terminology. The root path cost. Root path cost, that is the cost, the number of hops. Root path cost is the number of hops. Then there is the designated bridge and the designated port. Yeah? I will explain what a designated bridge is. The bridge. So for each LAN there is a designated bridge. This is the bridge that carries traffic towards the root, upstream in the tree. The port of the bridge where this is happening, that is called the designated port. And so each designated bridge for LAN has one port that's called the designated port. It can be a bridge can be a designated bridge for multiple LANs. As you see this here, in this case here, bridge number 2 would be designated bridge for LAN 3 and LAN 4, and these two ports would be called designated ports. Two designated ports, one root port, one designated port, one root port, just a root port. This one here this is a designated port. This one here is a designated port. This one is also a designated port. The root bridge doesn't have a root port. This one is a root port. That's essentially how this bridge works. Okay, so got this. All right. So now we're thinking now about sending BPDUs. These fields. These fields here are essential for building the tree. So when I write now a BPDU, I only write these 4 fields. And how the algorithm works is the receiver of such a message treats this number here, these 4 fields, as a number with 4 digits. Then, which allows a bridge to compare different messages. So this message here is interpreted as follows. I am the sender of this message. This is my ID. I'm sending this message through this port. It's not port, the port ID. I believe, this is a belief system, I believe that this is the root. And my cost to go to the root is in this field. You all see this? Okay. So, now, if a bridge receives VPDUs, it compares them in an order relationship and treats them like a digit, like a number with 4 digits. This is one number here, this is the second one. And then the bridge establishes kind of a smaller than relationship. It can say one message is smaller than the other one. And I use the less as indicating smaller. Smaller is better. Bridges always will want to find that they will always prefer, they always find that a smaller number is better. Smaller is better, yeah, for that. So, what is it? And what they say is smaller means it advertises a better path. It will always prefer something that is smaller, saying this is a better path. So, when does it say? Well, it first compares the roots. And this is how it picks the smallest root. If I get a message from two different roots, I would always say the one with the smaller number, R1, that's the better path. Maybe a longer path, but that's what the bridges do. Yeah? And that's how they agree on the smallest number. So, these are two messages being received. So, compares this M1 is a better message than M2 if R1 is less than 2. If they both advertise the same path, then C1 less than C2 is better. C1 is the smaller root path cost. So in this case, if a bridge receives two messages with the same root, that advertise the same root, you pick the one, you prefer the one that has the smallest cost. Now, if you receive messages that both advertise the same root with the same cost, you prefer to talk, you find that the bridge, this is the sending bridge here, the third field here is the sending bridge. You prefer the sending bridge with a smaller ID. That's just a tiebreaker, it's just breaking ties. B1 less than B2. Yeah. Now, if that's the case, if all three are equal, that means you're getting, a bridge now gets two messages from the same bridge, advertising the same cost. Then you prefer, you say, well, the smaller port number, that's advertises a better path. Yes?
So in the previous slide where you had the bridge 3 as the root bridge, how would that work? Wouldn't bridge 1 be the root bridge?
Let's see. Give me
depending on its MAC address?
This is the previous slide, but that's not what we mean.
He's talking about where the tree was constructed? Here.
Yeah, so I don't have port numbers in here, but let's go with it as far as we can. Let's suppose that port numbers are kind of starting with a clock and you're going. So, can you phrase the question?
No, I assumed bridge 1 would have ID 1. I was wondering why.
Yes. Not be the bridge, would not become the root. Very good. So that's the idea. Yeah.
So,
yes.
if you're manufacturing bridges, you'd want the lower ID ports to be the higher speeds?
Well, that is not a consideration when you build bridges. The only thing that we do is see at least these 2 bytes priority field. That's pretty much all that is done. And then it's up to the network administrator to configure these numbers. If they don't know how to configure this, they will all be preset to I don't know. They should be preset to FFFF. Yeah, I don't know what they're preset to actually. Or they should be, they're preset to 000. That would not be good. Because then you have to change the configuration of all other bridges. If you want to make one bridge the root, so the default here should be all ones, highest number, and then if you decrease the priority field is a configuration setting that's not set automatically. By setting that number small, you're making the bridge, controlling who becomes the bridge.
Okay. I was talking like near the end.
There may be some bump with the keys somewhere. Bump. No. Does it come from the speaker? Projector.
Everywhere.
I think the chassis driver.
I've muted everything.
It's the fan, you say that.
It's the fan.
Yeah,
Okay, I hear the echo coming from here. Thank you. Did I answer your question?
Actually, my question was is on the slide where we were, the selection of root.
The last one or the next one, this one?
The one before this? Yeah. So at the very end, when you get to the ports, the smallest port is selected, right?
Yes.
So like, if you have a...
It's just a type, you just need typewriters, that's essentially what it is.
Right.
Okay, you lose at this point, it's just, yes, it's also the bridge ID also, the only thing that can be set by the administrator are these two buttons in the beginning, this priority field.
Okay.
So that way you can decide which ports, which bridge is more likely to become, is going to be selected. Alright, so, now initially, let's now start. So we know how algorithms are, so now we built the tree. Bridges are turned on. Initially, each bridge believes it is the root of the spanning tree. That's how they start. Each bridge says, I'm the root of the tree. They haven't learned about anything else. Could be. Yeah? They don't know anything. So they send out a message on all their ports saying, yeah, this is bridge. I'm bridge B. I'm sending this through my port P. I'm the root. My cost of the root is 0. That's what they say. Everybody sends this out. And it's turning all bridges on. They all do this. So each bridge looks now, yeah, so all bridges are sending this, each bridge now looks at what's coming in, and it collects them and compares them. And it uses this relationship to it picks the message that is the smallest. And it does it in the following way. Each bridge has its own BPDU. Each bridge has its own BPDU. So B, if the bridge starts, B0B is its own ID. So now, suppose a bridge has the BPDU R1, C1, B1, and P1, or P1, the bridge has multiple for each port, it has one. Yeah, so this number is really not that important here, but it's R1, C1, B1. This holds, it says, I'm bridge 1. I believe R1 is the root, C1 is the cost. If now this bridge receives a better message, M2 being less than M1, then advertising a different root, then what it does, it says, well, I picked the smaller root, R2 being less than R1. I add 1 to the cost, because this is what was advertised to me. I add 1 to it, that's my cost. I'm B1, and this is the port to which I'm sending. Yeah? So the bridge receives the small BPDU that it receives. It will use the smaller BPDU to update its own BPDU. This was before, this is now. So this becomes the new BPDU of the bridge. And This, let's see, this BPDU may be sent out to the port. If a bridge has received messages if it receives messages on a LAN, it receives it through a port, it will send out its own BPDU only if its own message is smaller than anything that it has received. You only send a BPDU on a LAN if you are offering a better path. So on each bridge, the port where the best BPDU was received, that's the root port. In this case here, the port on which this message was received, that port would become the root port. So this is now what's going to take place. Say B has generated a BPDU, yes, for each port X. B will send this BPDU on a port X only if it's better than any BPDU that it has received from port X. This message is sent out only if its own message is beating any message that's currently out there. It can only send if you have something smaller. If there's nothing smaller, it will not send the BPDU, but it will keep on updating its own. Now comes the designated bridge. For a LAN, the bridge that sends the smallest BPDU on a LAN, that's the designated bridge. And the port where it sends it, that is the designated port. Yeah? And this makes sense if you're looking this downstream. Yeah? You're taking traffic and send it upstream towards the route only if you're offering the best path. That is the one who offers the best path. Well, that is the bridge that sends the smallest BPDU onto that LAN. Since you're only sending if you have the smallest, if you're sending, you have the smallest, you're the designated bridge. So that's how this works. Alright. So then in the end, once the algorithm converges, the bridges then decide that each bridge has a root port. The root port becomes part of the spanning tree. Designated ports are part of the spanning tree. Everything else is blocked. So what's happening is, the root port is part of the spanning tree. For each bridge, the designated ports are part of the spanning tree. All other ports are not part of the spanning tree. And so this is now being decided, it's now being built by putting ports into a blocked state or a forwarding state. If a port is blocked, you don't transfer messages on that port. Otherwise, if it's not blocked, it's put in a forwarding state. That's how this works, yeah? And so this example that we had earlier, so the bridge number is not for the question, but we can't buy bridge through the roof. Anyway, so in this setting here, you have the DR, and you can see that this port here is not a root port, and not D indicates a designated port, are a root port. Ports that are not designated or root, they are blocked, not part of the spanning tree. So kind of then this is then, with these R and D designation, you build the spanning tree. All right. What we can do, I'm not sure I can finish this though. What we can do is run an example. Yeah, let me see how this is. So here's the setting with 1, 2, 3, 4, 5, 6, 7 LANs, and we have a total of 7 bridges. Just some topology. Yeah, just nothing. So now what we assume is that the bridges, these are the IDs, 3, 1, 2, 3, 4, 5. The port numbers are A, B, C. We assume that A is smaller than B and that's smaller than C. And then we can just start and run the algorithm. Yeah? The way we do this, there's a tableau on the next side. So what we have is bridge 1, bridge 2, bridge 3, bridge 4, bridge 5, bridge 6. So let's start all the bridges up initially. Yeah, as I said, what we're going to do is initially, let's say t is equal to 0. What we're doing is some simplifying assumptions. We assume that all bridges are turned on simultaneously. Yes.
There's a bridge 7 as well.
And the bridge that is missing.
And there's no bridge 4.
There's no bridge 4. Bridge 5, 6, 7. Thank you. T equals to 0. So initially, each bridge creates. So what we're doing is we're tracking the BPDUs, and we're tracking also where the BPDUs are sent on. So initially, the BPDU of bridge number 1 is 101. Yeah, and kind of what I don't do here is I don't say for bridge number 1 it's port A and B. Yeah, it's implied if it's sent on this message is sent on port A. There's an A there. Sent on port B to B there. 101. This is sent on port. This message here is sent on port A and port B. Right? If the message is going out on port A, it's 101A. If it's sent on B, it's 101B. You with me, yeah? The port number. The last number here being the port number. This one being the port number, of course, depends on the port on which the message is sent. So if bridge 1 sends call on port A, the message is 101A, it's 101B. Yeah, so I pretty much don't carry these numbers. For 2, it's kind of, this is now 2 sends this message and it sends it out on, it has 2 ports, the message is sent on A and B. And we have 303, and this is sent on ports number ABC. Bridge number 5 sends 505, and 505 is port ABC. Port bridge number 6 is ABCD 606, and then we have 707, and this is sent on ABC. All right. So now all these messages are sent. So bridge number 6 will receive messages from bridge 3, from bridge 7, from bridge 1, from bridge 2, from bridge 5. All these messages come in. So each message, each bridge now receives all incoming messages, compares them in this way, and in this method here constructs its own new BPU. So let's now see what the result is after the first iteration. So at t equals to 1, that means everything has been sent, and we have made updated messages. So bridge number 1, well, bridge number 1 will remain 101. And it will send it on A and B, because 101, there will be no bridge that receives 303, 606, it receives from bridge 7, very interestingly, it receives 7, you see in this case here, bridge number 1 receives 707B and 707C. But none of them are smaller than its own BPDU. Nobody can beat 101, so it remains the rules. For bridge number 2 is sitting here. It receives 606 and it receives 505, but it holds 202. So it says, well, I'm the root. 202. The smallest I've received, and I'm the smallest one on the upper LAN and the lower LAN. So I send this on port A and B. Now 3 receives, it receives 101, that's the smallest one. And then it uses this step here, very simple, yeah, just 101, well, my own BPU, I have to add 1 to this. So 3 then says, I believe 1 is the, I agree 1 is the root, I'm 3, 1 is the root, my possibility is 1. And this message now is sent on
A and C.
B and C. A and C. Is that right? A and C. It's not sent on B because it's not the smallest one. But on B and C, it has not sent smaller, it has not seen smaller messages. It sends this now on port A and C. What happens to 5? 5 also receives a message. It receives this message 202.10.1. So it takes this one here and says this is 1 is the root 1, 5. So on which, where does it send out this message? It sends it out on port B and C, is that right? Yeah. B and C. And 6 also receives the message from bridge number 1. So it has 116, and bridge receives from here, kind of looking here, kind of looking at these messages here, so it's 303 is smaller. So it is essentially sent it out on A, C, and D. A, C, and D. And bridge number 7, does it get? Yes, it also is 117. And it sends it out on port A only, yeah? Because over here it receives the message. Now that's an interesting point. What is bridge 7's root port at this point? The root port is port B, because B is smaller than C. Both receives 101 on these messages here. It prefers, this one is smaller, it compares these two messages, so it prefers then to go through this port here, through this LAN here to reach 1. There's some subtleties. Yeah.
So at that point, port C of bridge 7 is blocked.
Port C is blocked. Yeah, all ports that are not listed here, they're all blocked. Okay. Let's see. No, these are the blocked ones. No, that is not strike that.
We don't know.
These are the designated ports. Then you add the root port to it. What is not a root port and not, these are the designated ports, that's blocked.
Great.
Yeah, so in this case you're completely right. C is blocked, A is not that blocked. Yeah. Alright. Let's see. So this is then with this round here. Let's do the next one. So what happens here is that here nothing happens for 1. Yeah, nothing will ever happen. So let's send on A, B. Let's look what happens to bridge number 2. Bridge number 2, it holds 202, it now gets a message here. What does it get from 6? 116, and it gets here 115. Both better, 115, 116, both better than 202. So 115 being the smallest one. So it says now, well, I now agree, 1 is the bridge. I'm still number 2, and my cost go to bridge 2. And it will send this out on which port?
No.
None. Because it has the message 122, that message is smaller than what it has seen here, which is 116, and which has seen here, it's 115. Yeah? It's the largest one. This is received, it receives this one, it receives this one. So what happens with 303? So here the cost does not change. Bridge 3 has received, I think A and C remain the designated ports. For bridge number 5 receives now, B and C remain the designated ports. 115. B and C, you have a question?
Yeah, doesn't bridge 3 receive 117?
Bridge 3 receives 117, yes, but 3 itself has, its number is 113, so B is 117, yeah?
Right, I want to block that port.
Which one?
Port A, I guess.
Port A, what?
Or
No.
same thing.
Now in here, what bridge sends is 117. Bridge 3 has 113. 113 beats 117.
Okay.
Bridge 3 beats bridge 7. Good. Let's see, let's look at bridge number 6. 6 receives, so it's this one, so this one here is 113. So this port is blocked. This one here is 115, which means 116. And so here, only port D remains for bridge 6. And for bridge 7, what we get is, for bridge 7, this port, none, yeah. For bridge 7, remains 117. I realize I'm a minute over, but I didn't want to interrupt this. So essentially now we're done, and we can compare this. I think we did this right. From this information now, we can now build the spanning tree. Yeah? We can tell what we have not carried. Carried was the root port, which is the port number where the bridge received the smallest DPDU. Yeah. Where was this number received? But here it was on port number, whatever port number here. This was 7 received it from here, 3 received it from here, 6 received it from here. So these are the root ports. Yeah. 2 accepted this path here, so that's the root port. The designated ports are the ports that where BPDUs are sent on. Everything that is not a root port and or a designated port, that's a block port. That's our tree. Isn't it pretty? And there's some aesthetic to this. It's a niceness algorithm. Actually, was devised by in a PhD thesis from 1980. Rutger Perlman wrote a PhD thesis at MIT. That was essentially the algorithm, which then became the standard. Not that it's a terribly complicated algorithm. So Rutger Perlman also wrote, she was very, the same books, but the 2 editions, a book on interconnecting networks. It's a beautiful book. It's written with a lot of humor. It explains the spanning tree. She even has a poem about spanning trees. Yeah, maybe I should read it. But that's very nerdy, yeah, but okay. So she received 2 years ago last year the ACM SICOM Award for that contribution. It's a tremendous contribution. Writing a PhD thesis, and it ends up being an all device. Okay, thank you very much. See you tomorrow. Sorry for running over, but you understand why I did that.
Some of the RFCs are also pretty funny.
They are
April Fools, yeah. They're the ones with the high latency networks.